we're very happy to welcome our own Dana Scott for some substantial proportion of the full history of Heyting Algebras today. Go ahead, Dana.
Thanks, Kevin, for the setup here. I have to admit this is an exaggerated title because I haven't been spending 70 years day and night thinking about Heyting Algebras. But when I spoke by video to the conference in Warsaw last spring, I gave the title 70 Years of Fixed Point Theorems. And the reason is that when I was an undergraduate here in 1953, I fell under the influence of Alfred Tarski. And from his lectures and his advice, not only did I learn about the Tarski-Canastri fixed point theorem, but I also read his papers about lattices and boolean algebras, and in particular about Heyting algebras. And so it's been since at least 1953 that I've had this introduction. So, and I'm giving a sort of historical review here because I've often remarked to people that I've discovered that if you live long enough, you become an historical figure. And so I'm going to try to fill in some of that here. So actually, lattice theory probably goes back to about Dedekind because, of course, in working with algebra, he thought of the lattice of subgroups of a group or the lattice of ideals of a ring as an important thing. Kronecker accused him of being too abstract. I wonder what Kronecker would think of category theory today. There. But a lot of development took place, and then it became connected with logic through Schroeder and Peirce, for example. And there are two very nice papers, and I'm going to make these slides available somehow, yes. So Rota and Greitzer both wrote nice papers about history of lattice theory in case you want to look up those kind of connections. Now, my connection came through Tarski, as I said, and he right away had me read Stone's paper on the representation of Boolean algebras. That was the first research paper I think I ever read. But in the late 40s, Tarski and McKinsey wrote about lattices and modal logic and intuitionistic logic. And as I said, that's where I first learned about these things here. Now, as a freshman, of course, I had the Birkhoff and MacLean algebra book, and I got to know Birkhoff very well in later life, and Saunders and MacLean as well. My first job after the PhD was in Chicago, where Saunders MacLean was, and that's also where I met Halmos, where he was when he was writing his book on Boolean algebras, have those connections. But very important through connection with Tarski is from Poland. Tarski's last student before he left Poland. He left Poland for a conference in Cambridge and then couldn't go back because of the war. Mostowski was his last student there in Poland and visited here many times. I knew him very well also from visits to Poland. And Mostowski had his two students, Rasiow and Sikorski, that I'm going to speak about. And I had the chance, I'll tell you, the role that Jaskowski proved in connection with Heyting algebras a little bit later on. So I have these Polish connections. I would like to point out from Rasiow and Sikorski's book, The Mathematics of Mathematics, one of my favorite quotations here from Goethe. Mathematicians are a kind of Frenchmen. You tell them something, they translate it into their own language, and then there's suddenly something else. And of course, we have Grothendieck to add to that, something else as well. Now, I also had lots of connections with Dutch school. I didn't meet Brouwer personally, but I did hear him give an incredibly boring lecture at Berkeley in the 50s. He lectured to the blackboard only, and no one understood really a word he said. But of course, it was in the late 20s that he began formulating his ideas about intuitionism. He also went over to prove very fundamental things in topology in about that time. My opinion is he proved all those things in topology to prove to mathematicians that he was a real mathematician, but he was really interested in promoting constructivism through intuitionism. But that's my own theory. But he also had very connections with philosophical groups at that time. Everett Bett, who proved a very interesting theorem about definability in first-order logic, wasn't so much connected with intuitionism, but he was very much connected with that school of philosophy in Holland that Brouwer likes so very much. I knew Heyting extremely well from many trips to Holland there, and two students of Heyting were close friends of mine, Troelstra and Van Dalen, and there are, of course, many, many other people and their students in Holland. I'm not mentioning everybody, but I just wanted to give you some sense as to when Brouwer started putting forward his ideas. And then Heyting, the Brouwer's student, then worked out the formalization of it. I don't think Brouwer was so interested in formalization, but of course we've been very much influenced by what Heyting did. And I'm not reading it here. I was surprised to find when I was doing a Google Scholar search that Alonzo Church wrote a very, very positive review of Heyting's work, and I copied it out there. Now, Stone's approach was from functional analysis, and his experience there, I'm sure, had him think one day, now I've been doing all of these things over the real numbers and the complex numbers. What if I did something over another ring, like the two-element ring? And then he proved the things because he knew about things like maximal ideals and so forth. He proved the things about Boolean algebras. Tarski would have discovered those things, I know, but Stone got there first, and Stone and Tarski were about contemporary on finding the connection with intuitionism, algebra of topological spaces, and there. So Tarski's early papers, and one that I read from 38 there was propositional calculus and topology. That shows how the lattice of open subsets of a topological space are a Heyting algebra giving you a model for intuitionistic propositional calculus. And I've made this very, very brief here. Recall that Gödel connected things by, first of all, pointing out that the not-not translation gives you an interpretation of classical logic into intuitionistic logic, and that the intuitionistic logic could come through the S4 modal logic, but Tarski and Stone thought of it more from the topological point of view. That is, the interior operation on topological spaces gives you a model for S4 modal logic, and so those people tied it all up. And then, as I say, I learned the actual details about Heyting algebras from Tarski and McKinsey. And then in the late 50s, about 1960, Mostowski pointed out that, of course, everyone can see, it's really quite obvious, that the rules of inferior and superior in complete lattices are the same as the rules of quantifiers. So why not use complete lattices for interpretations of quantifiers, first-order logic? And Rasioov and Sikorski carried that out. And other people, of course, made lots of related combinations. I'm not giving the whole history here. I asked the Polish people over and over again this: if you use complete lattices for interpreting the quantifiers for first-order logic, why didn't you go to higher-order logic? Because once you have that kind of interpretation of first-order logic, then you can think of arbitrary predicates with values in complete lattices. You can go to higher-order logic, because the higher-order logic will be governed by the same quantifiers. Why didn't they do it? And they didn't understand my question. No one ever gave me a good there. So after Cohen discovered forcing, Cohen was an enormously competitive person. I think the most competitive mathematician I ever found. I don't think he ever read any papers. He just proved everything for himself, as far as I could make out. For example, like he did Tarski's decision method for elementary geometry all on his own. And he was at Stanford, and he was very irritated by Pfefferman and Kreisel talking about proof theory. So he thought he would redo Gensen's consistency proof for first-order arithmetic there, which he did for himself. And then he said, I'm going on to second-order arithmetic. And that's when he discovered forcing, and then led to the interpretation there. So he was lecturing on forcing, and Solovey, who had his first job at Berkeley, came to Stanford and heard it. And then he told us one day, I remember the day with a group, probably with Pfefferman, and we were talking to Solovey, and he said, well, look, what Cohen has done here could be reinterpreted by using the forcing to give boolean values to formulas of set theory. And so I went home. That was the end of the semester. And over the New Year's thing, I said to myself, wait a minute, we had all of this stuff from Rasioov and Sikorski. Why can't we go backwards there, not go from Cohen to Boolean, but why not go from Boolean to Cohen, simply give Boolean-valued interpretation of set theory? And Solovey was incredibly angry with me. He said, I thought of that myself. He had said it the other way around, but then he said, and then we sort of had a peace treaty and wrote a joint paper together. Cohen came first, and then that suggested looking again at Boolean values, and a lot of people have there. Now, in the 70s, when I was at Oxford, we had a very good conference on application of sheaves with many people from category, famous people from category theory there. And I think Mike Foreman and I wrote a very, very readable paper about sheaves and logic, and I recommend that. I think it's still very readable if you want a fairly gentle introduction to a number of things. Okay, how are lattices defined? Everybody knows that probably. If you can think of a partially ordered set, of course, the partial ordering has all the properties of reflexive and transitive and antisymmetric properties, and you have meets and joins, soups and imps in that. And of course, you could axiomatize that purely as a binary relation because the various elements are 0, 1, and the meets and joins are uniquely determined by their properties. You could also axiomatize lattices in terms of equational theory there because you just take the 0, 1 laws for the neutral elements, idempotence of the meets and joins commutative, associative, and absorptive laws, and then the partial ordering is recaptured very simply by equations there as you like. Now, lattices are not necessarily distributive, and if you want to torture beginning students with lattice theory, tell them how to prove that if you assume one distributive law, you can prove the other distributive law. If you have one with meets over joins, you'll be able to prove the other distributive law too. And of course, there are very simple examples to show not all lattices are distributive, as that example shows with the same x, y, and z. To try to fill it into the equations I wrote up there, you see the equations fail in that lattice. Now, Heyting algebras come in by adding implication to it, and in terms of the partial ordering, the key axiom there is the first if and only if there. And let me point out how things to say this here. Y arrow z is the maximal element x satisfying that second inequality. That's what it says. So you needn't have maximal elements satisfying it, but if you always have maximal elements there, that uniquely determines the implication operation. If you have a Heyting algebra with one implication operation and another implication operation, they're the same operation because it's the maximal elements satisfying that partially ordered thing. And you could also define Boolean algebras in terms of implication to. A lattice is a Boolean algebra there. And we know the properties of negation too if you would rather do that. But now the key thing is that a Heyting algebra is always a distributive lattice. You don't have to assume the distributive law because I gave a quick proof here. Through monotone properties of the lattice operations there, you have certain inequalities there, but then you can move things back and forth across the less than or equal to according to the axiom for Heyting algebras there. And so you move things out of the way and you do a little bit of junk, and then you move the thing back again, and lo and behold, you have a proof of the distributive law there. So that implication allows you to sort of expose things, do something with them, and then tie them up again, and so you get the proof of the distributive law that way. If you want to axiomatize Heyting algebras equationally, like we did with lattices there, then these are the principles there about how implication is related to the two sides of the arrow there, and then the implication distributes across and. Implication does not distribute across or across join. You have to be careful of that. However, the distribution of implication is the other way across or, but then you turn an or into an and. That's provable from the equations there. You don't need it as an axiom, but those are the equational axioms for implication. And actually, they're pretty closely related to axioms that Heyting gave originally for logic there. And I found out that the NLab site has lots of interesting background. If you want more axiomatic discussion of these things, it was an interesting place to find easily on the internet. Now, what is a complete lattice? We all know that. It has arbitrary joins and arbitrary meets there, which are characterized uniquely in the partial ordering there. And those are very much exactly the way we treat quantifiers as well, thinking of exists and or. And of course, it turns out that if it's complete in the sense of or or join, it's complete in the sense of meet, and conversely there. So you only have to assume one of the axioms for completeness to get the other axiom for completeness. And what is a complete Heyting algebra? It turns out that they satisfy an infinitary distributive law for meet across join. And the proof of that distributive law, you can do it exactly the same way I did it for finite meets and joins. You can do it for finite meets and arbitrary joins. The dual law is not provable in complete Heyting algebras. And once you have that distribution, you have the definition of implication, because the implication is the maximal element satisfying the inequality that's there. And so the distributive laws will get you the principles of arrow if you assume you have a complete lattice which has that infinitary distributive law, then it has both finitary distributive laws, and you can define implication to get everything you want there. So you can take that. Okay, why doesn't the dual distributive law hold in complete Heyting algebras? Do you know any complete Heyting algebras? Well, let's take the open subsets of a topological space. That's a complete lattice. Do they satisfy that distributive law? Of course, because in open sets, meet is intersection and join is union. So of course it satisfies that distributive law. Why do the open sets not satisfy the dual distributive law? Can anyone give me the example of that? I'm sorry?
With infinite intersections or what?
Meet, infinite meet. You have to be careful what meet means. Meet is the greatest lower bound, okay? So maybe I could write it on the board, but maybe I'll just do it by hand waving here. Take the open set from minus n to 0, okay? And take the open set from plus n down to 0, but leave 0 out there. So take the union of those two open sets, okay? Over all the n's, what's the meet of those things? You see it converges down to 0, but you left out 0, so the meet is empty. Now if you take another open set that covers the 0 and take the join, on the one side the join will be empty, and on the other side the join will be different. So you have to be careful of that. Right? The join will be the extra open set that you put there to cover the origin there. And so that's because when you take intersections of open sets, you have to leave out some limit points in doing that. So that's what you have to be careful of with topological interpretations of these things here. And a finite distributive lattice is always a Heyting algebra, because a finite one, if it satisfies the finite distributive laws, when you take the infinite distributive law, it's not infinite at all, and you already satisfied it. So finite distributive lattices are Heyting algebras, uniquely Heyting algebras. There's only one way to make that into a Heyting algebra, where the arrow is the maximal element satisfying that inequality. And of course, you can make up a lot of pretty pictures of distributive lattices. For example, you can make towers. Just pile one on top of another. Here are a couple of things piled on top of things. You can keep doing it in various patterns there. There are an awful lot of finite distributive lattices. Now here is what I learned from McKinsey and Tarski, their papers of 47, 48, is why equational theory of Heyting algebras is decidable. If you take the equations for Heyting algebras the way I gave them, if you search for proofs and at the same time search through finite distributive lattices, either you'll find a proof or you'll find a counterexample. Okay? And here's the proof. Imagine that an equation fails in some Heyting algebra. In other words, imagine it's not provable. I mean, provability is being true in all Heyting algebras or in the free Heyting algebra, for example. So let's take the other case where the equation has failed in some Heyting algebra. So think of a valuation in that Heyting algebra. That Heyting algebra may be infinite, but think of an evaluation of that equation. We're making a substitution, one substitution into the equation so that it fails, but we see that in the two polynomials, rho and sigma, there are only finitely many sub-expressions. So think of the finite number of values you need just for those sub-expressions. They generate a distributive lattice by successively taking meets and joins. Now, some of the sub-expressions are arrows. Those arrows satisfy a certain maximality condition in the whole algebra. But in the subalgebra generated by the values of the sub-expressions, they'll also satisfy the maximality condition. So in other words, in that sublattice, finite sublattice, those few arrows that occurred in rho and sigma will get their correct values. So therefore, you have a finite counterexample to the equation. If it fails in some Heyting algebra, it fails in a finite Heyting algebra. Am I convincing? Now, Jaskowski, he was about of the same age as Tarski. I met him once on a visit to Poland. He pointed out that you don't have to look through all possible finite Heyting algebras, but you can generate a sequence of them, and then he proved, he didn't prove it too well actually himself, and later people gave a better proof of the thing, that there's a sequence of finite Heyting algebras. Unfortunately, they grow with double exponential growth. You take the nth Jaskowski Heyting algebra and you take the nth power of that, and you get this lattice, and now you add one more element to the top. Because you can stack Heyting algebras on top of each other, you just stack one thing on top there. That will be sufficient because you'll get more combinations at the next step when you take the direct products. And so that sequence of things is proved, was proved from Jaskowski to be characteristic of the equations of the Heyting algebras. But it isn't particularly practical because it's double exponential size. Gödel was asked, I think, by Hans Hahn in Vienna back the year I was born, was asked whether there's a finite matrix or finite interpretation of intuitionistic propositional calculus, and Gödel answered in the negative there. You can't have a finite Heyting algebra that exactly characterizes intuitionistic logic Heyting algebra equations. For example, if you have a Heyting algebra with m elements there, take m plus 1 variables and think of a substitution for those m plus 1 variables. If you have only m elements, then 2 of the variables have to get the same value. So therefore, that polynomial will come out to be 1. But if you take a linearly ordered Heyting algebra, you can take 0 to k for any k there as a partially ordered set. If you take a linearly ordered Heyting algebra, it has a very, very simple implication. You can figure it out for yourself how the implication behaves. So if you take a linearly ordered Heyting algebra with more elements there and make the substitution on the lower elements in the Heyting algebra, it won't come out to be equal to 1. You can, if you have more than m elements and take a substitution there on just the first m elements there, the value will turn out to be smaller than 1. And so, therefore, no finite lattice can be characteristic for intuitionistic logic. What, did I make it clear enough? Is it okay? I discovered there's lots of new material that I didn't know about. Kostadoshan was my student and Michael Dummett's student in the late 70s in Oxford. And he went on to work in proof theory, but he wanted to do categorization of proof theory, and he wrote these 2 books. I have the books in the other rooms if someone would like to look at them. Alas, he passed away in 2017. It's very sobering when your students pass away before you do. But he had time to do a lot of interesting work in relating proof theory in the style of Gensen to category theory. So have those 2 books. I also discovered, and so I gave references to those 2. You can look at the slides later on. I also discovered that Peter Gibson, who's a professor down in Southern California, has interesting books on varieties of lattices, particularly residuated lattices, which have interesting connections with category theory. And I have the orange book there in the other room. Unfortunately, the yellow book costs $150. I have a Kindle version of it, and I have a PDF version of it I could share, but it's just outrageous what our favorite publishers are charging for books these days. Peter Gibson is an interesting guy. We might want to ask him to give a talk to Topos some time, so you can look at his books, and I can share the expensive book with you there. But I just discovered very recently, by again doing Google Scholar search, that Roy Dieckhoff reviewed a lot of things from Gensen proof theory because he wanted to implement Gensen's cut elimination, which is a syntactical process of working backwards. You're trying to prove something and you say, well, what did I need to prove this? And then what did I need to prove those things to prove that, you keep working backwards. And so Roy Dieckhoff has investigated in quite some detail. Alas, he was my student with Peter Collins in set theory in Oxford in the early 70s, and he passed away in 2018. He was a long-time professor in St. Andrews in Scotland, and he wrote an extremely nice paper on the Gensen things, and I found today that there also, if you do the Google Scholar search, or I have his obituary with references in it, he did more things there. So you see, he wanted to see why there, with Gensen's method, there is a termination of the procedures, and also if it doesn't terminate in a proof, how you get a counterexample. What I told you about finite Heyting algebras is not practicable because it requires double exponential size of lattices. He also wanted to make sure that in doing the backtracking that you don't fool around and go directly to where you want to go. And also he tried to simplify from taking the classical system, starting with what Gensen and Heyting did, to have simple systems as possible. He was a very, very good author. So he went to a lot of trouble to implement things in Prolog, okay? But that was back in the 10 years ago, okay? So I think there might be something interesting to do to look at the implementations from some more modern systems, maybe connected with computer algebra or things. And so I have the references there, and as I said, a very, very nice, I have a very nice obituary of Roy, which gives all the references to his work there. So that's my review of history, and I didn't know I was going to talk this fast. I'll just have to tell you a joke here. This is awful. Wait a second here. I have to tell you a joke then, because I've already gave my talk, and look what time it is. Oh, I'm sorry. I thought it would take much longer.
Well, we should have interrupted you.
Maybe you should have interrupted me. So here's my joke that I found today. This is, can you see the New Yorker has a caption contest there. I hope I win the caption contest, because that's what I thought of when I saw that the witch was looking at her iPhone. I've told you my favorite joke about the iPhone, that the father is reading a story in bed to a little girl, and the little girl is doing this on her iPhone, and the father says, "Stop that fact-checking. This is a fairy tale." Okay, I'll stop there, and glad to take questions. Yeah.
So about that double exponential construction.
Yes. Oh.
Isn't that in some?
Oh, my legs are hurting me. Can you give me a chair? Oh, wait. Must have been standing in a funny position here. You can close the top. Yeah. Oh. Evan, stand up here and hold me here for a minute. Yeah. Oh, my leg. Ow. Oh, gosh. I stood too long in one position here. This is a bad lesson to learn. Ow. My leg went to sleep, in effect. Ouch. Okay. Yes, what were you asking?
Well, about that double exponential construction for
Yes.
finite Heyting algebras that you were, in some sense,
Yeah, yeah.
Propositional intuitionistic logic.
I have some, yeah. Well, I mean, it's both classical logic and intuitionistic logic. I have exhausting in the sense of strength, exhausting decision procedures. So, and intuitionistic logic is worse. And so people have worked out what the complexity
So
is
that
of
was
that.
Statman's result, right? So
And Statman has one, and other people too. And I found some references too. So I can find them again. There are papers about the complexity of the decision method. Yeah, yeah. But Roy Dickoff had some good ideas also for the proof theory there of trying to make things somewhat more efficient. So things may be very bad in general, but it may turn out that for special cases, you can do pretty efficient proofs for special cases, yes.
I have some other thing to say, but I don't want to monopolize as a guest here.
Carry on.
So actually, have people ever considered the dual of Heyting implication? So the dual of Heyting implication can be seen as some kind of common generalization
Yes.
of the...
Peter Gibson has a lot of it called residuated lattices.
Is that what it is?
Yes.
Okay.
And of course, stop to think for a minute. A finite distributive lattice is also a dual distributive lattice. So it has two implications, looking up and looking down.
Okay.
Yes? So there are lots of examples of that dual kind of residuation. It's a kind of not complementation, but a kind of subtraction.
Right.
There.
So
Yeah.
In a contrived by database practice situation, people have tried to look at the common generalization of subtraction of sets on one hand, and on the other hand, on proper subtraction of natural numbers, the so-called monus operation, which is minus. And it turns out that there is some literature on that. So, and what's
Well, that
interesting
book of
there
Peter
is that
Gibson, that book of Peter Gibson really covers a wide. He's done a lot of effort on that. Just those things, yes. Why do you like them?
So the natural numbers do not form a lattice or even a semi-lattice. However, the additive monoid of natural numbers has a property that that is the order in the additive monoid of natural numbers can be defined as some people call it natural order. Am I the only one who has encountered this? I mean, it's not totally clear what's natural about it, but that's what they call it. And so people have considered commutative monoids, which are not idempotent, but in which the order defined by saying A is less than B, if you can add something to A to get to B exactly. So they call this thing natural order. And in such structures, you can define the dual of Heyting implication, which they called in general monus, as exactly with the dual of your if and only if situation. I mean, of course, you recognize, everybody does recognize the categorical situation. There's an adjunction there and so on. So
Does it work for cardinal numbers? Because infinite cardinal numbers aren't linearly ordered unless you have the axiom of choice. So is there anything interesting with cardinals?
Possibly. I've only seen it in this context, in the context of generalizing just these two examples. But here is the interesting thing. Just like Heyting algebras can be axiomatized algebraically, as you showed us, commutative monoids naturally ordered with monus, they have an equational axiomatization that was derived by somebody that whose name I only learned by chasing, name of Bosbach. Does this ring a bell? Bosbach? It's okay. So this does not. It's an interesting generalization, and that's because in databases, people consider sets with multiplicities. Elements of the sets have multiplicities, the so-called bag semantics of databases. For purely practical reasons, it's too expensive to eliminate duplicates. And so this is of some interest in the corners in which I've been working on database provenance.
Why don't you send me a pointer to something typical there? Send me a pointer to a paper that you can find.
Yeah, I can send you a pointer to, I think, an article in Algebra Universalis. The Bosbach article is in German, and I know very little German. You know maybe a lot more than I do. It's a very difficult paper. That axiomatization seems to be a tour de force with long derivations and so on. I can send you a pointer.
Thanks.
Got a question. Speaking of the adjunction hiding behind the definition of the implication, the hiding implication in a complete distributive lattice.
Yes.
I think it's perhaps not ahistorical to say that that definition of the implication as a least upper bound is first instance of an adjoint functor theorem, because this formula is essentially the formula that comes out of it. Do you know much about this history, whether Dan Kahn and Fry were getting inspired totally from abelian categories and topology and things, or whether the logic actually...
Well, it must have, it must have come much earlier from algebraic topology. I mean, Eilenberg and Steenrod were already talking about adjunctions, I think, in algebraic topology.
Yeah. I think that Kahn actually defines adjunctions in general in the rather late 50s, a little surprisingly maybe, but...
And Kahn was very important too, the Israeli Kahn. Yeah, but I think that was already in the air when Levere started thinking about, so to speak, more axiomatic presentations. But I think the algebraic topologists had already thought of the need for those, I guess.
Another book, but Peter Johnstone's stone spaces, in his beginning in the introduction and so on, he discusses that, what you just discussed.
That's a good point too, yes, right. Peter Johnson was very much influenced by Saunders MacLean. Saunders and MacLean sort of took him on as a not as a student, but he mentored him very, very much in the beginning of his career. He suffered terribly from COVID. He loves singing in choruses, and so with his Cambridge chorus, they made a trip to the States in the early time of the pandemic, and he came back and he almost died from COVID.
It's always been curious to me that lattice theory, which seems a very beautiful and important subject, is not really taught in that, for example, standard undergraduate curriculum except through maybe topology or Galois theory or something. That's not quite lattice theory either. And what of the history of the last 70 years has meant that lattice
Well, I certainly learned about it in the Birkhoff-MacLean book, which was already out in about 1950 or so. But that's because Birkhoff was thinking about lattices.
Right.
So probably, and then, but I seem to feel that people who discuss the lattice of subgroups of a group or the lattice of ideals of a ring do say things about lattice theory, but are maybe just happy with only working in those two examples as necessary rather than abstractly.
Right.
Yeah.
Seems interesting to me as sort of an accent of the undergraduate curriculum, that seems very common. I don't know. My other question is, what are the next 70 years of Heyting Algebras? Do you have any comments?
Well, okay. I recommend looking at Costa Dawson's books. Alas, he died, and he can't answer any questions now, but he did spend a lot of time talking about categorization of proof theory. So I don't know what could be achieved with that, but he spent an awful lot of time thinking about it. So that's where I would look next. In other words, he's really looking at functors and that sort of thing from the point of view of principles of proof theory. So let's look at that and see if there's something new to do with that. I would think that would be the best step. He even says the word categorization, I can't say it, of proof theory. So let's see how far he got with that, okay?
Thank you.
You know, on a related note, I know vaguely what cut elimination is in proof theory, but the title of one of these books was cut elimination in categories. Do you know what is meant by that? Cut elimination in a category?
Well, I can't bring it up here now.
Yeah.
The book is just around the corner there.
Okay, all right.
So
Well,
you could sneak it out overnight and
sure.
see. But I also wrote a brief thing about it as a kind of abstract of the book there. Where are the slides going to be available?
They will appear right next to the talk announcement on the seminar page
As soon as you can get them there.
tonight.
Tonight, okay. Okay. But you can find his book just
Okay.
around the corner there. And so that's what I was just saying to Brendan. I think that's the place to look because he thought of the need to make the connections. So let's see how far he got with it. That's what I meant.